Our next presenter is Dr. Geoffrey Thyne. He graduated from Texas A&M University in 1979 and began his career as a research geochemist at the ARCO Oil and Gas in Plano, Texas. He received his PhD in geology from the University of Wyoming in 1991 and taught at California State University on Bakersfield at the Colorado School of Mines until 2005. He returned to the University of Wyoming in 2006 at the Enhanced Oil Recovery Institute. And today he is the Chief Technology Officer at the Engineering Salinity and an expert in increasing oil recovery by manipulation of water chemistry. Dr. Thyne will present to us low salinity water flooding. What do we need to do to move forward? The economic case. He will tell us about current terminologies and summarize the current knowledge with the major challenges to widespread development and provide detailed economic evaluation of a large-scale low salinity water flooding project. Thank you very much, Dr. Thyne, for being with us today, and thank you very much for your presentation.
Thank you all for being here. My name is Geoffrey Thyne. I'm the Chief Technical Officer at ESAL, which is short for Engineered Salinity. You can see in back of me. I want to acknowledge my co-authors today, who have really done most of this talk. I'm just kind of presenting the information they put together. The title of our talk is Low Salinity Water Flooding. What do we need to move forward? The economic case. My co-authors are Alireza Bigdeli and Vladimir Ulanov. And this whole thing started about 2 years ago when Alireza sent me an email and we started talking about low sal and the future of low sal and why low sal isn't more popular as a enhanced oil recovery technique or an improved oil recovery technique. So the promise of low sal water flooding for the last 15 years has been this technique, whether it's EOR or IOR, that can be employed at any stage in hydrocarbon recovery. It can be used in conjunction with other techniques. It's very desirable because of the low cost of the operations. That is, we're simply modifying the water chemistry of a water flood. There's little to no environmental impact, and we have a vast experience in the industry with water flooding. And as a kind of metric of how interesting this topic has been, there's been 360 papers in the last 4 years, including 16 review papers of the 360 papers and all the papers that came before that. So obviously it's a fascinating topic and one of great potential import for the oil industry. So what are the outcomes of low salinity water flooding? This graph over here on the right is a compilation, not a complete compilation, but a compilation of a lot of results, both from experiments and field experiences between 2004 and 2014. And what we can see here is there's a wide range of recoveries. And I counted the zeros, that is a negative result or no result. We'll talk about negative results later, but no results. I included this in this compilation. And up in the upper left-hand corner of this figure on the right, you see two histograms. And a fascinating point, one's for sandstones, one's for carbonates, the blues carbonates, the brown sandstones. We get about the same wide range of recovery. And this was all triggered, all this research was really triggered by BP in the Kuparuk Reservoir, sandstone reservoir on the North Slope. And back in 2005 was their first reported and published work. And they got 10 to 15% of the original oil in place as additional recovery. So this is a tremendous number. Average recovery worldwide is about 35% at the end of water flood. So we're talking almost half again as much potentially that you can get out of both carbonate and sandstone reservoirs. Shell in Syria, published in 2010, they got 5 to 15% OOIP. That was in another pair of sandstone fields. And then there was an EORI, that's Enhanced Oil Recovery Institute of Wyoming study, in 51 fields in another sandstone where there was no additional recovery. And so both this chart and those words speak the story of low sal. which is sometimes it works great, and that's got to be a big up, and sometimes it doesn't work at all. And that's the real problem of low salinity water flooding, is how do we get rid of the zeros and move to the 10s and 15% recoveries? So first thing is we got to know how it works. And that has been an ongoing debate, incredibly large debate. We do know that it works in sandstones and it works in carbonates. We do know it doesn't always work. And so the mechanisms are unclear, but this table over on the right-hand side kind of summarizes a lot of work. And what we see is that pretty much in the recent 4 to 5 years, people have centered on wettability alteration as the key mechanism. Surface reactions and multi-ion exchange could be seen as another form of wettability alteration, or another way to say wettability alteration. And I think we get into this very large debate, which that's fine, but at our company, what we're interested in is results. So while we can continue to debate the mechanisms and do lots of experiments and do these things, what's going to be important is to find a way to move forward functionally and make this process work economically. So where are we today? Well, we have inconsistent results. That's both capitalized, and it's important. Inconsistent results in both the laboratory and field. It's long and expensive to screen, test, and model. The industry average is 3 to 5 years and costs millions of dollars. And the project economics have been rather opaque. I mean, there's just not a good paper we can go find with actual case histories where we can compute these economics, because in the end, deploying any technique in the field is going to come down to economics. Over on the right-hand side, you see Eni's workflow for screening a field. So screening is just not executing it, just figuring out, is it going to work and what's the benefit going to be, so we can do some economics and get management to approve it. And you can see they have 8 steps here. In fact, you circle back on some of these steps. Some of these steps are quick, some of these steps are long. This is why 3 to 5 years to look at a field and decide whether it's going to be worthwhile is the industry standard. And that's not a very effective standard. So what do we need? If we're going to make low salinity water flooding work, what do we need? We need predictable results. We need fast screening and laboratory testing. And we need transparent project economics, costs and benefits. You've got to be able to go to management and tell them what the benefit's going to be and what the costs are going to be. So we really need to engineer the salinity of the water flooding. That's a thing that we talk about at our company. Other people may talk about it differently, but in the end, you need to know what that target salinity is, what it's going to cost you to implement it, and what the benefit's going to be. So this is one flow. This is a flow that we use at ESAL to engineer our salinity. We do screening. You see over there on the left-hand side, we take a lot of information and empirical relationships that we've developed, use those to move on, say, yeah, there's no problem here, there's no red flags, let's move to laboratory testing. We do laboratory testing, it's fairly fast. What we're looking for is wettability alteration. So we moved beyond arguing about mechanisms and said, yeah, it's wettability alteration. Can we measure wettability in the lab quickly? Can we look at the effect over there on the right-hand side in that diagram of salinity on the x-axis and wettability on the y-axis? And what we believe is that neutral wettability is where we produce the most oil. So that's our target. And what you see here is an actual case history. The current water was what they were injecting into the reservoir. We found that the target water was a different salinity. We can move the salinity at the surface with injection and move the salinity in the reservoir, thus altering the wettability and increasing recovery. That basically is what our company is about. And I think that's basically what low salinity water flooding is about. But let's get to the good stuff. So how well does it really work? What's the real advantages? How much money can you make? So we went and found a set of case histories This is a set of conventional fields in North America. They initiated normal water flooding, reinjection of produced water in the 1980s. And then in around 2010, a decision was made on the corporate level, we're going low sal across the whole field. No preparation, no laboratory tests, no screening, none of that. They were convinced that this was going to work, they were going to do it, and they did it. And they did it in 7 fields. They injected with low salinity water 5,000 TDS from groundwater sources, and they took all the produced saline water and re-injected in a different interval. So this is a clean sweep kind of scenario. They saw responses within 9 to 12 months of the start of injection of low salinity water flooding. It continues till today. So now we have a 10-year history on changing the water chemistry across your whole field. And I want to emphasize there was no testing or planning. It was just, we can get this low salinity source on site. We drilled some water supply wells. We plumbed up the surface differently, and off we went. So let's look at some of the results. What we see here, I've labeled the fields, sanitized this a little bit as you might expect, A, B, C, D, E, F, G. And the green fields were the ones that showed a positive result of some level, and the red field, it's very interesting, showed damage. We actually made the production worse by using low salinity water in this one field, and we'll see in more detail how that worked. What I want you to really look at here is the primary plus secondary recovery. This is pre-low salinity, and this is projected out. If you hadn't done anything, let's take it out to the economic life of the field, what would your recoveries have been? And as you can see, there was a wide range of recoveries in these fields, and that's not atypical. This is all in the same formation. It's pretty similar oil chemistry, pretty similar water chemistry, so the expectation was that all the fields would work about the same. The first thing we see is that's not the case. The second thing we see for low salinity water flooding, projecting out the benefit to the end of the life of the field that is now apparent, what we see is the recovery in percent OOIP range from about 1.1 up to 15.8. So back to that original diagram, we've got the full range of low salinity water flood effect apparent in this set of 7 fields. In some cases, by changing to low salinity water flooding and getting a better decline curve, you extended the life of the field. That's the last column. And we can talk about that in more detail in the next couple of slides. And then in the bad case, where they damage the wettability in the field, they actually reduce the field life by almost 25 years. And that's a pretty significant finding, one we didn't really expect, to be perfectly honest. But the data is the data. So let's take a close look at the data. What you're going to see here on the left-hand side is our laboratory testing, and on the right-hand side, the actual case history in the field. So this is a case where there was a benefit, and we see there at the bottom where the water source was changed, about the middle of the diagram. And you can see a well-established decline curve on water flood in the brown line, and then it's extended out. You can see where it would have been. And then there's a sharp break, and the decline rate changed from 16% to 10%. So a real benefit. We will, by the end of the life of this field, see an extra 5 million barrels. So that's a pretty substantial increase. And over on the left-hand side, you see the laboratory testing that we do anyway. What you see here is wettability on the x-axis and residual saturation on the y-axis. This curve that you see, the shaded curve, is the standard data from starting in 1950 all the way through the present. Hundreds of data points on this plot that are covered up with the shading, showing that the best recovery, or the lowest residual saturation, is at neutral wettability. And so what we saw in this particular case is the original wettability there in the red dot is somewhat water wet. By shifting to lower salinity water, you move to more neutral wet. And on the right-hand side, you see the proof of this idea that we can measure wettability in the lab and relate that to increased recovery. In fact, we predict about this recovery. So we feel that this is a really good technique to move forward with low salinity water flooding. You've got to test your water You've got to see what the wettability shift is going to be. You've got to optimize that wettability shift and get your maximum recovery. In this case, this was not optimized for maximum recovery, but still an excellent result. But what about that bad case? So the same setup here. Over on the left-hand side, we see the results of the laboratory tests. What we're basically predicting by the shift in wettability to more water wet from fairly neutral wet is a decrease in recovery. And what we see over here on the right-hand side is the decline rate changed from about 6% to almost 12%. So we left in the red shaded area all that oil behind. We essentially left 16 million barrels behind by the time that this field will be shut down and reach its economic limit. This is what I would call wettability damage. You moved the wettability the wrong way. This was a one-size-fits-all solution. So that was the major problem. You didn't do your examination and your due diligence beforehand with your laboratory testing. If they had done that, we would have said, no, 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 no. Do not go to a lower salinity water. This is not always the answer. And I think that's been one of the problems with low salinity is we've tried to find a one-size-fits-all answer, and it doesn't work that way, unfortunately. It'd be great if it would. And you can see some of the numbers. There's economic numbers associated with how much money have we lost, how much have we decreased the field value. We're going to publish all this in a paper, so there'll be plenty of time to get into details when you see it all in a paper. But I can assure you that these economic models are very well done. They're very tight, and these projections are pretty sound. So what did we learn out of all this? The diagram over on the right-hand side has three columns, primary and secondary, that is operating the field the way you normally would. This unoptimized low salinity water flooding, which overall did produce more barrels of oil. You can see we went from about 250 to about 275 million barrels of oil by the time these fields have reached their economic life. That's a modest improvement. The OOIP for these 7 fields was about 1.2 billion barrels. So 25 is not that exciting. And then the last column is what could you have gotten if you tested all the fields ahead of time and optimized the wettability like we do for the maximum benefit. And you can see that that's a much better scenario where you're picking up, you know, about 125 million more barrels of oil out of the 7 fields. So what did we learn out of our study on the economics of low salinity water flooding? One thing that we didn't really touch on, but if you go back to the table, you would see it, and I'm happy to go back if we have time, is that low salinity water flood results are proportional to standard water flood results. Meaning, if you have a really good water flood, you're going to get a bunch more out of a low salinity water flood. If you don't have a very good water flood, you're going to get more, but not a huge amount. You're not going to double it or something like that. In general, this 5 to 15% bracket is where you want to be. And most of that is tuning your wettability, getting your wettability to the best possible point that is practical and economic for this field. So good low salinity water floods are profitable for the most part. I don't think, you know, again, you've got to do an economic evaluation in each case, but for the most part, that's going to be true. A bad low salinity water flood can be pretty darn costly. It's kind of a new thing to recognize that maybe you don't get a 0, maybe you actually get a negative result. That's not something that we would see in an experiment, the way the experimental protocols go. So I think that's something we've missed up to this point that we can now drag out of this field data. And it's a really important point. And the other thing we see is that really every field needs a engineered salinity water flood. So rather than just saying it's just 5,000 TDS or below 5,000 TDS, you have to actually consider how you're shifting wettability. Where do I want to get to the optimum? What are the economics? You have to engineer the salinity of your water flood. So thank you all for your time today. My co-authors and I thank you for taking the time to listen to this presentation, and I look forward to any questions you may have.